How we doing, everybody? Here we are. We're almost we're pretty much halfway through, our time here, and so we're going to start chapter 8 today. Chapter 8 talks about testing hypothesis, and what we're going to do is first go over our learning objectives. So the first learning objective we'll begin with here. It basically states to understand the logical framework of tests of hypotheses, to learn basic terminology connected with hypothesis testing, to learn fundamental facts about hypothesis testing, to learn how to apply the 5-step procedure for test of hypotheses concerning a population mean when the sample size is large. Remember, what is a large sample size? As a reminder, that would be when n is greater than or equal to 30, then we can say that our sample size is large. To learn how to interpret the result of test of hypotheses in the context of the original narrated situation. To learn what the observed significance of a test is, to learn how to compute the observed significance of a test, to learn how to apply the p-value approach to hypothesis testing, to learn how to apply the 5-step test procedure for test hypotheses concerning a population mean when the sample size is small. Remember, a small sample size would be less than 30. And then to learn how to apply the 5-step critical value test procedure for test of hypothesis concerning a population proportion, and to learn how to apply the 5-step p-value test for test of a hypothesis concerning a population proportion. Okay, was it the same thing? Did I just repeat the same? Oh, this was the critical value, and this is the 5-step p-value test. Okay, so that was the difference. So first here, types of hypotheses. So there's 2 specific types of hypotheses that we're going to talk about here. The first is what we call the null hypothesis, and it is denoted by H sub 0, and it is the statement about the population parameter that is assumed to be true unless there is convincing evidence to the contrary. So we'll always start off with a null hypothesis, a hypothesis that basically the question that's being asked is assuming to be true. But then we'll also have an alternative hypothesis. And this alternative hypothesis is denoted by H sub A and is a statement about the population parameter that is contrary. So it is essentially the opposite of the null hypothesis and is accepted as true only if convincing evidence is in favor of it. So if we can essentially reject the null hypothesis, then we can say that the alternative hypothesis is true. And so now we need to talk about hypothesis testing. So hypothesis testing is a statistical procedure in which a choice is made between a null and an alternative hypothesis based on the information in a sample. The first step in hypothesis testing is to identify the null and alternative hypothesis. So being able to read a question and say, this is H sub 0, this is the null hypothesis, and this is H sub A, this is the alternative hypothesis, right? The end result of a hypothesis testing procedure is a choice of one of the following 2 possible outcomes, right? So the first outcome is to reject the null hypothesis and therefore accept the alternative hypothesis, or fail to reject the null hypothesis and therefore fail to accept the alternative hypothesis. So that wording there is key, and it's important for you to understand that as we move through these problems. So here's an example for you. So a publisher of college textbooks claims that the average price of all hardbound college textbooks is $127.50. A group of students believes that the actual mean is higher and wishes to test this belief. State the relevant null and alternative hypothesis. So here is our conclusion here. So basically, the null hypothesis is that the mean, okay, the sample mean here will be $127.50. Since the student group thinks that the average textbook's price is greater than the publisher's figure, the alternative hypothesis in this situation is that the alternative hypothesis is that the mean is greater than $127.50. Okay, So what we have here is we have kind of a graph, and this is we're calling it our density curve for the mean here. So here would be our mean if H sub 0 is in fact true, okay? And so the logic of hypothesis testing, the test procedure is based on the initial assumption, all right, that the null hypothesis is in fact true. If the alternative hypothesis, H sub A, has the form of this, where the mean is less than the hypothesized mean, then we're going to reject the null hypothesis, okay, if our sample mean is far to the left, okay, of our hypothesis mean, all right? If the null hypothesis has the form of the mean is greater than the sample mean here, or the hypothesis mean, then we're going to reject the null hypothesis if the mean is far to the right of the hypothesis mean. And if the alternative hypothesis, H sub A, has the form of H sub A, where the mean is not equal to the null hypothesis mean, then we're going to reject the null hypothesis if the sample mean is far away from the mean of the null in either direction. So, we have all these if-thens. If, then we're going to do this. If, we're going to do this. So we got to look at the ifs, we got to see what we get as a result, and then we have to produce the then here, right? And then we have the rejection region. So if the alternative hypothesis has the form of the mean is not equal to the null mean, so the mean of the null hypothesis, the test is called a two-tailed test, right? So if it's not equal to, then we're talking about the two tails on either end. If the alternative hypothesis has the form of it being less than, then we're calling it a left-tailed test because it's going to be less than that value. And if it's greater than, then we're going to have a right-tailed test. So right now, we're taking a look at this would be our left-tailed test, right? So if it falls in here, we're rejecting it, right? Reject, this would essentially be our rejection region, okay? Over here, this would be a right-tailed test. If it falls here, then this would be our rejection region, greater than that value, okay? And then we have our two-tailed test. So if it falls in either this region or in this region, right, not equal to, then, we would then reject the null hypothesis. And so we have two types of errors here. In a test of a hypothesis, a type 1 error is the decision to reject the null hypothesis, okay, when it is in fact true. I have a chart here that I'm going to share with you on the next page that will help you to organize this. It's, again, one of those things that I strongly recommend that you copy and paste, you cut, you take it out, and you put kind of in a study guide. A type 2 error is the decision not to reject the null hypothesis when it is in fact not true. The number alpha is used to determine the rejection region, is called the level of significance of the test. It is possible that the test procedure will result in a type 1 error. So this is the chart that I was referring to here. A standardized test statistic for a hypothesis test is the statistic that is formed by subtracting from the statistic of interest its mean and dividing by its standard deviation, okay? So this represents, basically when the test statistic has the standard normal distribution, we would have here our alternative hypothesis, terminology, right? This has to do with the rejection region, and then this is when it doesn't have a normal distribution, but it has a t distribution. Then this is how we would go by that. Obviously, we'd be using a standard normal table here for problems like this, but in this particular case, we would be using that t distribution table. Okay, so systematic hypothesis testing procedures and the critical value approach. Identify the null and alternative hypothesis. That is first, right? So this is our 5-step approach. So the first, we want to identify the null and alternative hypothesis. Next, we'll identify the relevant test statistic in its distribution. Next, we're going to compute from the data the value of the test statistic. And we're going to go through this with an example problem so that you understand it, but knowing these steps, very, very important. Construct the rejection region. So this is where we're going to draw that bell curve. We're going to draw our curve, and then we're going to sketch out and shade the rejection region. And then we're going to compare the value computed in step 3, that's the test statistic, to the rejection region constructed in test 4, and we're going to make a decision. Are we going to accept? Are we going to reject? What are we going to do? Okay, so the standardized test statistic for the large sample, and this is something that we already discussed. This is really nothing new. Remember, we were calling it E essentially, or actually we weren't calling it E. We're calculating a z-score, or a value that we're going to go ahead and plug into our table. But this is what we've calculated. I believe it was in chapter 2 when we calculated z-scores here. Okay, so we can say if the standard deviation is known, then we can say that our z-score is going to be the standardized test statistic, or it's going to be our initial value minus the mean divided by the standard deviation over the square root of n, which is our number of sample, our sample size. Next here, if the standard deviation is unknown, then essentially what we're doing here is we're using the population standard deviation instead, and that's going to help us to calculate it. The test statistic has a standard normal distribution. So because we're dealing with z here, we can say that this has a normal distribution. Okay? So here's an example, right? Here's an example we can run through, and we're gonna do the work on it right now. And by the time we're done with this, we'll probably be ending this video and maybe moving on to a live one that I'll sketch out for you. So a cosmetic company fills its best-selling 8-ounce jars of facial cream by an automatic dispensing machine. The machine is set to dispense a mean of 8.1 ounces per jar. Uncontrollable factors in the process can shift the mean away from the 8.1. So there's obviously error in that machine, right? A little bit more might come out, a little bit less might come out, and cause either underfill or overfill, both of which are undesirable. In such a case, the dispensing machine is stopped and recalibrated. Regardless of the mean amount dispensed, the standard deviation of the amount dispensed always has a value of 0.22 ounces. A quality control engineer routinely selects 30 jars. So this is, remember, we're taking a sample, and they do this all the time. So they're doing this over and over and over again, selecting 30 jars here, selecting 30 jars here, selecting 30 jars here. All right, to check the amounts filled. On one occasion, the sample mean is 8.2 ounces, and the sample standard deviation is 0.25 ounce. Determine if there is a significant evidence in the sample to indicate at the 1% level of significance that the machine should be recalibrated. Okay? So the first thing we need to do is identify what is our hypothesis and what is our null hypothesis. So our alternative hypothesis. So we have our null hypothesis here, which is 8.1. Our alternative hypothesis is that the mean is not equal to 8.1, and we're saying that alpha is going to be with a 0.01 significance. So the sample is large, right? Because we are choosing a value that is over that 30, right? Or in fact equal to that 30 here in this particular situation. And so the first step is to go ahead and calculate our z-score. We know it's large, so we're going to go ahead and calculate the z-score. And when we do, we get 2.490. Now this is what we're going to go and put into our normal distribution table. So step 4, since the symbol H sub A, or the alternative hypothesis, is not equal, then we can say this is going to be a two-tailed test. If it was less than, it's a left-tailed test. If it's greater than, then it's a right-tailed test. But since it's not equal to, then it's a two-tailed test. So the critical values are going to be both plus or minus, okay? Plus or minus z sub 0.05, which from the last line in the table, 12.3, we read off is 2.576. And so that's what we get here. Notice we're going negative infinity all the way to negative 2.576. And then we're going from 5.576 to positive infinity. Okay? We have a chart here that's going to show this particular piece in it. Okay? And then we can conclude that the machine does not need to be recalibrated here. The data does not provide sufficient evidence at the 1% level of significance to conclude that the average amount dispensed is different from 8.1 ounces.